All right, so let's pretend we're in lab together. I'm coming to you live from the organic lab, not live, live on tape. And I'm going to do the calculation that we would have done together if we were actually in lab today. And that is, if you remember last time, we decided we needed to use Spartan to look at the energies of the two possible products. We used the cis principle and the fact that the stereochemistry of the dienophile is preserved in a Diels Alder reaction to come up with the fact that for our reaction we predicted two products. And we decided that one way to determine which of the two would form, because remember, Diels Alder reactions are stereo and regio specific, only giving one product. So we wanted to be able to predict which product would form. So to do that, we decided we needed to build those two possible products. And remember, one had all of the substituents in the Diels Alder addict cis to each other, and we called that all cis. And we had another one where the two sets of substituents were cis to each other, but then the two sets were trans to each other. Okay, so we're going to set out to build those compounds. Now, at this point, when you watch this video, we will have already discovered that something has happened to our initial addict. And so what I'm going to build for you is what the actual new predictions would have been when you sat down to actually do this calculation. Okay, and so to do that, I'm going to build this first, the all cis. So I'm going to go over here to rings. I'm going to select cyclohexane because that's the one part of my adduct. And I'm going to use these two carbons as the one that the substituents go on. And then this is where the double bond is going to be. So I'm going to come over here and select sp2 hybridized carbon because I want to basically rehybridize these two so I can have the double bond between them. So I'm going to click on those atoms, and now they're both sp2 hybridized. So I'm able to come up here to the bonds and actually make a double bond. So now there's a double bond there. And so that means that now these two carbons are where my substituents are going to go. Okay? And so to do that, I need to put an sp3 hybridized carbon on both of these positions. So there and there. Okay? This one is the methyl group, so it's going to stay as it is. This is the CH2 that we decided actually, initially had the OH on it, but then after the rearrangement, once the reaction occurred, it made a bond with a carbonyl that was on this carbon. Okay, so to do that, I need to actually put an sp2 hybridized carbon here, right? Because that's going to be where the bond is to the carbonyl. Okay, so I need to put my OH on there. I'm sorry, my oxygen on there, which is sp3, and I'm going to put it here. Okay, and then on this, we're going to have the carbonyl that was there from that anhydride ring. So I need an sp2 hybridized carbon attached here. Okay, and I'm going to have a bond between these two, here to here, and then I'm going to have my sp2 hybridized oxygen, which is the carbonyl there. Okay, and then that means on this carbon, and it has to be, remember, cis to this, is where I have my carboxyl substituent. So again, I need an sp2 hybridized carbon. And I need a carbonyl, so sp2 hybridized oxygen, and then I need the OH. Okay? And so now that looks really messy, but let's go ahead and clean it up by doing the energy minimization on it. Okay? And so that's what this looks like. And we can kind of, I'm going to move this around where we can kind of see what's happened. Okay? This is the methyl group, and it's cis to the CH2. Here's my double bond. Here's that ring that's formed between what was the OH and the carbonyl, which opened this up to give the carboxylic acid. And the energy that it gave for that has disappeared, so I'm going to hit energy again. It's 23.9687 kilojoules per mole is what that says. 23.9687 kilojoules per mole. So that's what you'd write down as the energy for that all cis. Okay? All right? Now, once we have this made, remember we talked about the fact that we're going to determine whether this was the actual product that formed by looking at the J values. And the J values, as you've discovered by now, are related to geometry, and so they're related to dihedral angles. So what we need to look at, remember we identified that the dihedrals that are important was this proton that's attached to the methyl group, this proton that's attached to the carboxyl, this proton that's attached to the carbonyl of this new ring, and then this. And I think that the way we had it labeled, this was A, B, C, and this one was, I think, H. I wish I had my notes with me, but I'm pretty sure that's how we identified it. So what we need to do is we need to look at these dihedrals between these two protons, between these two protons, and between these two protons, because that's going to be data that we need. Okay, so I'm going to measure that right now. And I'm going to do that by going up here to this tool, which measures the dihedral angle. So if I click on this icon, and then remember 4 atoms define a dihedral angle. So 1, 2, 3, 4. That dihedral is minus 37.14 degrees. Minus 37.14 degrees. Okay? So that's one of them. Then we want to measure the dihedral between these two. And so these are the 4 atoms, here to here to here to here. So that's between A and B. And it's 34.47. And then we want to look at the one between, I think, pretty sure that's H and A. Here to here to here to here. Minus 16.70. So those are my dihedrals. And as you will have discovered by now, we're going to use those dihedrals then to be able to predict what the J value should be if this is in fact the product that forms. Okay? So there's that data. You know, it's recorded on this video, so you can watch this again to see how we did it for the all cis. Well, now what I'm going to do is I'm going to go back to where I can build, and I'm going to redo this where I change the stereochemistry of this. Okay, and I think probably the best way to do this is start over. Just go out of Spartan and get back in, and then I'm going to build my structure again, and that's just to make sure that, you know, again, it'll show you how we did it. There's the cyclohexane ring. Need to change these two to sp2 hybridized carbons. connect the pi bond, so I have a double bond there. And now these are the two carbons that the substituent's gone, and now I need them to be, cis to each other, but I have to make the substituents here cis to each other, but trans to these. So I'm going to go ahead and make these cis the same way I did before. There and there. So this is my methyl group, and this is the CH2, because it's going to be attached to the oxygen that's going to close the ring. Okay? And that means that this carbon here, I can go ahead, that's the one that's got the carbonyl on it, but I'm going to be using these two valencies on these two carbons because I need it to be trans to these two. Okay, so my carboxyl group on this carbon is going to be going down. So I'm going to go ahead and put that in there. And then here is the valence I need to connect to for this. So that's going to be a carbonyl, right? And then this needs to be connected to this. I'm going to build my bond. That's that O that reacted with the carbonyl carbon, right? And then this will be a carbonyl also. You'll have time to rewatch this to make sure. And so now I'm going to hit the energy minimization to clean this up. And let's just double check. Methyl group is cis to the CH2. They're on the same side. But now this bond and this bond to what was the anhydride are in both pointing in the opposite direction. Okay, so this is the other possible product that we talked about. And when I do the energy minimization, I'll do that again. The energy is 107.1081 kilojoules per mole. 107.1081 kilojoules per mole. Okay, so that's the energy. We have that to compare to the previous case. All right? Now, just like we did before, if this were the product that was forming, we said that the way we would determine that is looking at the J's. Okay? And so I would need to measure the J's. And remember, just to get us situated, this is A, and this is the B proton, and this is the C. This is the one that's geminal to the methyl group. This is the one that's geminal to the carboxyl group. This is the one that's geminal to the carbonyl of the new ring that's formed. And this is the one that's geminal to the CH2 that was an OH before the rearrangement. So H, A, B, C. And so we need to do our dihedrals like we did last time. Okay, so I'm going to start with the C to B dihedral. I'm going to measure that. There to there to there to there. Minus 92.66 is what the angle is. Okay, now I'm going to do B to A. Okay, so to do that, it's going to be here to here to here to here, those four atoms, right? So here to here to here to here. Minus 55.01. And I'm sorry, my nose keeps coming into the camera. All right, and then the last one is going to be A to H. Okay, and so I'm going to do that here to here to here to here. And it's 177.95. Okay? And so using those J's, 177.95. So in your data for your paper for these two possible products, you're going to have the three dihedrals that are what's determining, the stereochemistry. So when we're looking at the geometry of this, what's important is how the methyl and the CH2 of the cyclohexene ring is related to the two bonds from what was the anhydride. So that's all the data that we need from these two things on Spartan. And so I'll make this video available when we have had our initial discussion tomorrow, and then you'll be able to use this data to actually get to the answer. Okay? So hopefully this is helpful, but of course, we'll be meeting synchronously to discuss this video after you've watched it. So hopefully you'll be able to understand that. All right? And that's all we have there for the Spartan.